Okay, hi everyone. Thanks. Sorry I couldn't be there in person. So I'm going to talk today about my group's work with DiffuserCam. This is a term that we invented, but it's related to a lot of ongoing research in lensless imaging. And I'm going to talk about how we get it towards multidimensional imaging, largely using ideas based around compressed sensing. So, whoops. So I think probably everyone here knows what computational imaging is, but I like to give just like a baseline of like what's my idea of my definition of computational imaging. So it's this idea that you design your imaging system, software and hardware together. So you have, this is just a canonical example here of lensless imaging. So you have a camera and you took off the lens. So it's really just a sensor pointed at the world. You take a picture and it looks just like garbage because you didn't have that sensor, this lens there to focus the light. And if you think about it, the lens's only job is to bend the light rays in a particular way. But the light that hits the sensor in this picture is the same as the one if I had put the lens in there and formed a proper image. So the question is, can I computationally bend those light rays to get back the image from this information? And practically the answer is really no. But DiffuserCam is all about like you can put something in the imaging pathway, not a lens, but this is a diffuser. So it's just a bumpy piece of plastic. Like sometimes we literally use Scotch tape or those stickers that you put on your window for privacy so your neighbors cannot see in. And we simply like place it on the cover glass of the sensor. So it's sitting like a few millimeters usually from the sensor surface. And then I take a picture, which also looks like garbage. But now it's structured garbage, and computational imaging is all about saying that, okay, now I've put in something in my hardware that gets the information into my measurement, then I can computationally solve an inverse solver to get the final result and reconstruct my scene here. So this is kind of like the main idea of DiffuserCam, and I think it's a really nice platform example of computational imaging. Design process about how to design hardware to get the like problem like invertible or solvable. Is the diffuser a good thing to put in? Well, it's cheap and simple. It makes the camera really compact because you can put a lot closer to the sensor than you would have otherwise put a proper lens that might have been like out here. So there's some benefits to it. And the final result, though, is going to definitely have artifacts. So there's also some drawbacks. And you need to think about your application space and when it makes sense to do this. So let's look into how this DiffuserCam works. So a regular camera, you have a point in the scene, and your lenses bend the light rays such that that point maps to a point on the sensor. So you put your camera in focus, and all the points in the scene map to points on the sensor, so you get like a copy of the scene onto your sensor. So then if you have that point in the scene and you take a picture, we would call this the point spread function or impulse function of the system. It looks like a dot here, but it would really be like a diffraction limited area pattern. And you may or may not care about diffraction effects, depending on if you're doing photography or microscopy or something in between. So this DiffuserCam, instead you have the diffuser or scattering element a lot closer to the sensor, and a point in the scene then spreads out and passes through the diffuser, and then the diffuser has some random bumps on it that will cause the light to focus in some areas and be defocused in other areas, and it creates this random caustic pattern. This is called a caustic pattern. It looks like the bottom of a swimming pool on a hot day. It's the exact same idea. And so now, this is our point spread function. So a point in the scene, excuse me, now maps to this weirdo caustic pattern, which is really big. And normally you want your point spread function to be as small as possible so that your captured image looks as close as possible to the scene that you're trying to image. But now it's very different that you've got this gigantic point spread function, and that's why the measurements we take look really blurred, because you've got all these overlapping point spread functions from lots of different points in the scene. But we can undo this computationally. And you can think about this in terms of this is your point spread function, and this is a bad point spread function because it's big. But Is it a bad point spread function? So if you think about like what spatial frequencies exist in this point spread function, if you were to take its Fourier transform, you will see that it still contains a lot of high spatial frequency information. There's like sharp lines here, and in fact, these are diffraction limited line widths about spatial frequencies all the way out to the diffraction limit, which means you have a chance to reconstruct the image up to that resolution limit. It'll be diffraction limited, basically like with a numerical aperture set by the size of the sensor. Okay, so we really do just literally make this with double-sided Scotch tape sometimes and cheapo sensors. So you can make this thing really cheap at home for fun. We have a tutorial on our website of like how to build this like for fun in your house. I had two awesome undergrads who put this all together. And people have tried it and sent me their images. It's really fun. If you do it, please let me know. And people use this in classes to help teach computational imaging and linear algebra, because that's how you solve this problem. But most of the stuff I'm going to show you uses a much fancier sensor and like a more carefully designed diffuser. So okay, so you got this point source and it creates this caustic point spread function. If I move my point source around in the scene, what happens? Basically, it's the same point spread function, but it shifts with respect to where the point in the scene is. So this is a shift invariant system. It's not exactly shift invariant, but it's largely shift invariant. That was by design. If you turn on two point sources in the scene, what you get is a linear sum of the intensity point spread functions for both. So that makes us a linear system in terms of intensity, which means we can write this as y equals ax, like a linear system. So a traditional imaging system is also a linear system in the sense you have some measurement y, some scene that you're trying to measure x. So you might take your scene and raster scan it into a vector here. And so this measurement is just a simple linear transform of the scene that you're trying to image. And this A matrix describes that linear transform. It basically is your system matrix describing how your system maps the scene into the measurements. So for a traditional camera, optical engineers have spent centuries, literally, trying to design imaging systems that have A matrices that are as close as possible to the identity matrix, because that will exactly map your object onto your measurement. And then you just capture your image and you don't need to do anything else. When we talk about computational imaging, we don't need that A matrix to be an identity matrix. It can be anything as long as it's known and invertible. And so our measurement also need not look like our final result, because we can do an A inverse effectively and solve for X. I'm going to talk a little bit more about what this A matrix can be or is for our situation, but it's not arbitrary. You do have to think about making this known and invertible, and that's not always easy. Okay, so here's our raw data and then our recovered scene, another prettier image, and then a video. And I like to show this video because it has lots of artifacts, and you can see very clearly like there's weird stuff going on here. It has a lot of like pretty global artifacts and weird things going on because of the nature of how you capture this data in one form and then do this inverse problem. So these artifacts I do think are addressable. I think if you spent 10 years perfecting how you glue the diffuser onto the sensor and how you calibrated it and how you make sure that nothing heats up or changes after you calibrated it, I think you get rid of most of these artifacts. And you might be able to get to a point where you could compete with like your iPhone camera, for example. And then you could make more compact cameras. I don't know that they'd actually be cheaper, because these like cell phone cameras are already plastic molded lenses that are dirt cheap to make in mass production. And so we didn't really want to compete in that space against, you know, decades of optical engineering. And we wanted to look for things that this thing can do that other cameras cannot. But first, let me get into a little bit about the details of the reconstruction. So if you have a point in the scene and you move it around, so do that again, as it moves laterally, then the point spread function shifts laterally. So this is because the system is shift invariant. So that means that this A matrix is actually a convolutional matrix. So it means that every column of this A matrix represents the point spread function for a given point in the scene. So this is like the central point in the scene point spread function. And then if I move my point over here, this point spread function shifts. And basically what it does to the A matrix is that everything just shifts. So there's also cropping happening. I'm just going to ignore that for the sake of clarity, that if you read our papers, you can figure out how we actually deal with that. But basically, this A matrix is a convolution. So every column of the A matrix is the same as the previous one, but shifted. And so there's really no need to measure the entire A matrix, and there's no need to like try to like measure the surface shape of that diffuser. We can just take a single PSF measurement, like put your iPhone flashlight far away in the far field and take a measurement of that point spread function. And that's enough to fully characterize this A matrix and be able to solve this inverse problem. The other beautiful thing about this A matrix being a convolution is that it means there's really no need to actually instantiate this matrix. Like this thing is gigantic. So we have, say you have a 1 megapixel center, which is pretty low number of pixels, then A will be a 1 million by 1 million in size. And it's humongous, and trying to invert this humongous matrix is just like really painful computationally, but doing a deconvolution of a single PSF image is very efficient computationally. It's just 2 FFTs and a multiplication. Okay, so we're basically just doing a deconvolution. We also incorporate this cropping. So it's a little bit more complicated than that. But we implement it via an iterative inverse algorithm. So an optimization problem where you have this measurement Y and you're trying to minimize the difference between the measurement and the expected measurement. So you have some estimate of X that you're trying to update, and then you put it through your forward model. So you just convolve it with your forward model here. And then you're trying to minimize the difference between these two, or the error term, subject to some constraint. So one, that we need it to be positive intensity. So these are intensities. So we need it to be positive. You can't have negative intensity. That's just non-physical. So we just enforce that as part of our optimization. And finally, this term here is often used as in this case, it's used as a regularizer. Later, you're going to see that it's really necessary and to allow us to do multidimensional stuff. But basically, lambda tells you like how strong this term is, and then it tries to find solutions that are sparse in some basis set. And you get to choose the basis set. Maybe it's just like native sparsity basis. In most of the images I'm showing you, we use TV, or total variation, which just means the gradient of the image is relatively sparse. And that's a pretty good regularization parameter for natural images. We solve this all with ADMM, really popular optimization solver, because it's pretty fast and it works well for this. In Halide, this is just to use our GPUs really efficiently and get the hardware working well. Okay, so I'm going to call this like the physics-based or model-based image reconstruction way of doing things. You put in your measurement, you solve this optimization problem, and you get out your image at the end. The other way you could do this is deep learning. So everyone's into deep learning now. So like, forget about all this physics that we know. We don't need to model it. Let's just put in a whole bunch of input-output pairs and train a neural network that can learn the input-output mapping. And you can do that. But we wanted to think about this a little bit more carefully rather than just saying, oh, deep learning can do it, so let's do it. So I like to think of these inverse problems on this spectrum between like model-based or physics-based. This is like the ADMM, gradient descent, like these iterative optimization solvers versus deep learning. And the physics-based stuff is very interpretable and robust, but it can be slow and it has some weird model mismatch. You saw some of those artifacts earlier. And the deep learning stuff can be really good at getting rid of those artifacts. And it can do really fast reconstructions, which is really important too. You can get to like real-time based. We can already do real-time based for 2D deconvolutions, but if you want to do 3D or anything at fast frame rates, then deep learning can make it go faster. But it also has these problems that it's not very interpretable, not always robust, and you need training data. So what we wanted to do was something in between this, sort of physics-based learning is what we call it. And there's a lot of people working towards this ideas in various different areas. But it's basically amounts to designing a neural network whose architecture is based on this iterative optimization algorithm that basically defines, so you define the architecture of the network based on the physics that you know. So you're taking the physics that you know and incorporating it into this neural network, and it makes the neural network really efficient. So you can use a lot less training data. And then you're using the information that you know and learning the stuff that you don't know, which I think just sort of like academically is really satisfying, because you're not throwing away known information about the physics, but you're letting the deep learning do what it does best, and that is to like learn the stuff that you don't know how to model. Okay, so this is sort of the architecture of the network. So we basically take that iterative ADMM algorithm and we unroll it, meaning that like we make a deep neural network where each layer of the network is one iteration of that optimization. But then we can create a loss function and do updating and learn all the different parameters of that ADMM optimization. And this is a really nice, efficient way to like put a physical based model into a neural network, which is otherwise pretty opaque on how to think about doing that. So it's called Unrolled networks, physics-based algorithm. So Christina did this work. You still have to train it, but you don't need as much training data, like thousands of images. So she put a display screen so that she could train it on a lot of images at once. And then she took images with DiffuserCam and a regular cam to train the network. And once it was trained, she could just use it on the DiffuserCam images and get reconstructions. So here's the ground truth image that you start with. And here's the reconstruction if I just do the physics-based, like ADMM, the physics-based reconstruction. So it's slow and it has a lot of artifacts. If I do pure deep learning, so forget all the physics, so give it a lot of training data, I think 24,000 images, then it's fast, but it has different artifacts. And then if I do this hybrid physics-based learning stuff, it's fast enough to be real time and it has the least artifacts. You get the best quality. So I think this is a really nice example of neural networks working together with physics to do better than either could do alone. Okay, so cute, but what's it good for? And certainly this DiffuserCam has gotten this question that it's fun. It's a cool example of what computational imaging can do. But as I mentioned, we're just not really ready to compete with like Apple iPhone cameras for a lot of reasons, even if we can make things smaller and maybe cheaper. And so we wanted to think about things that we could do that other cameras truly cannot do. And one of the things that we got after was this multiplexing idea. So if you think about, like, you've got your scene out in the world, every point in the scene spreads out before it hits the diffuser. So that's why you have this large point spread function for every point in the scene. And that's also why your measurement looks like garbage. It just looks all like blurred out. But because every point in the scene maps to a large area on the sensor, it means that you can just like delete an area of the sensor, and as long as every point within this black box has a point spread function that spills out into the area that is measured, then you have a chance to reconstruct the image without that big missing hole. Okay, so this is a form of compressed sensing because you're solving for more things than you measured. But this idea that like it's tolerant to erasures, that if you don't measure things in some areas, you can still recover information about the image in those areas because of this large point spread function. And we say like this large point spread function I'm talking about as a multiplex measurement, in that every point maps to a lot of pixels on the sensor. And that's like what makes it work. So you could delete 90% of the pixels in your measured image and still be able to reconstruct the scene pretty well. And this is something a regular camera certainly cannot do. If you don't measure a pixel, it's gone. So we wanted to try to like leverage or exploit this idea to do something useful. So one of the things we started with was to say like, okay, if I have a point off up here, so the point is here and its point spread function is large, so some corner of the PSF still makes it into the measurement, even though the point is outside of the field of view of this system nominally. And so we said, oh, well, now we can reconstruct those points out there because we have information about them in our measurements. So we tried this, and this is our like nominal field of view of this is like the sensor size, where the sensor maps to. And indeed, we can reconstruct some stuff outside of the field of view, outside of where the sensor measured, which is pretty cool. But as you can see, it's not very high quality. So in some areas it looks okay, and then it's just garbage in a lot of other areas. So we kind of gave up on this idea, this like extended field of view imaging. It's just like not a good, it's not very, works very well. But one thing that you can do that we found was that we can use this to build a humongous imaging system, an imaging sensor. So we took like each and we put them in an array. So you put these sensors as close as possible together, and then they still have a huge black space in between them because you just can't physically get them to be like touching each other. And so people don't build large area sensors like this because of this black space in between. But now we can say like, well, as long as the point spread function is bigger than this gap, we can have a chance to reconstruct everything within this blocked off erasure area and reconstruct this whole gigantic image that's like tens of megapixels large. So our sensors only actually cover 8% of the total area. And so there's a lot of like leveraging now of this regularization parameter that enforces some sort of sparsity so that we can do this. And it works really well. This is just a simulation, but we actually built this thing. Actually, this is another 2 undergrads built this thing. So it's a 2x2 array of sensors. We put a big diffuser in front of the whole thing, and then they take these images that are just like these four sensor measurements, and then they can reconstruct this much larger thing. So this is 3,500 pixel by 3,500 pixel image, and they can reconstruct like a cal that actually exists right here in the middle where they take no measurements. But because it has a large point spread function, we can get it back. And here's an X. This is a really like a very prototypey experiment, but it demonstrates the possibility to go after large aperture imaging with very flat optics, because to make the image bigger, to have like this bigger format image, we don't need a bigger lens. We don't need to put the lens further away. It doesn't get heavier and more expensive. You just tile all these sensors sideways. So I have a postdoc now who's working on this with a really fancy sensor array and like a more carefully aligned system to try to see how we can push the limits on this. Okay, but I think like the heart of the things that we did with this DiffuserCam was to take 2D measurements and try to reconstruct 3D quantities. So scenes, XY time is a 3D data cube, and XY lambda is a 3D data cube. And I'm going to talk about each of these in turn. So 2D to 3D. If we have a 3D scene, so our X now is 3-dimensional. So it's, say you have a 1 megapixel sensor, then 100 different depth planes, then you're trying to solve for 100 million things. So now X is a vector of 100 million things. We're still going to take this like 1 megapixel measurement, the same as before, but now we're going to try to reconstruct 3D instead of 2D. So we have this 100 million by 1 million A matrix that consists of a bunch of convolution matrices. And what happens as you move your point spread function to different depths, you just see that point spread function scaling. So that takes care of the calibration and computation problems, but we're still trying to solve for 100 different depth planes from a single image. So it's a severely underdetermined system. And that's exactly where compressed sensing comes in. So normally people are used to thinking about image compression in terms of taking an image and trying to compress it down to an image that fully represents the scene without loss of information, but with less data. So we can try to do this now. We're doing this now in the capture stage. We take this single 2D measurement and if the scene is sparse in some basis set, then we can solve that optimization problem with the regularizer and be able to reconstruct 3D from this 2D measurement. So we take this measurement and reconstruct this 3D scene, little leaf, and I'm just showing you the 3D reconstruction spinning around to give you depth information. Okay, so this is cool to me because it gets at this like space bandwidth product problem. So in microscopy, you always want large space bandwidth products. Space bandwidth product refers to like the number of things you can resolve. So if you have high resolution,
Laura?
yeah.
Laura. Yeah. Sorry to cut you off, but we're having a bit of a sound problem. Can you mute yourself and unmute yourself to see if it solves it? Yeah, sorry.
Does that help? Can you hear better?
No, sadly no, but I think we're just going to continue. It's okay. It is what it is.
Sorry.
No.
I don't have any ideas. Sorry. Okay. Yeah, so if you are trying to resolve an image, then the number of things you can resolve is basically the space bandwidth product. So if you have high resolution across a big area, you have a large space bandwidth product. If you have high resolution across a small area, you might not have a large space bandwidth product. So if you're doing like point scanning microscopy, then you can get a large space bandwidth product simply by scanning over a lot of points, but it comes at the cost of speed. If you go to like light field microscopy, it's single shot 3D imaging, but it has terrible resolution, so your space bandwidth product is really low. So we're here dealing with basically single shot, meaning we always have good speed, but then like what our space bandwidth product can be really now depends on how sparse your scene is. So if your scene is extremely sparse, you can really get best of both worlds, fast and high space bandwidth product. As your scene gets more and more dense, your possible resolution drops and you get down towards this light field area. So here's an example of a microscope version. This took a lot of engineering to get this going because a lot of our assumptions start to break down when you go to microscopy, and then you have to deal with color filters for fluorescence. But Grace was able to build this like single stack of things on top of a sensor and make a flat diffuser microscope. Then she puts her sample directly on top of it. This is zebrafish, and what you're seeing are like whenever a neuron fires, it lights up the brain. So we're seeing individual neurons firing here within the zebrafish's brain, and this is the idea of our collaborators want to study how those neurons fire and relate to each other, and they need these fast time scales of single shot imaging, but now they can get it all in 3D. We built another tiny microscope based on the Miniscope, which is a really popular open source microscope platform from UCLA. And this is just convenient because people are already using these Miniscopes. They're like smaller than a quarter, you can see here. And the objective is just this little stick here is basically, it's a grin lens. That's the objective for the microscope. And it's a terrible objective. Miniature microscopes simply can't do aberration correction because they don't have enough space. They can't add extra optical elements. So you have this terrible objective lens, grin lens, but you can implant it into the mouse's brain and watch neurons firing while it's running around in a maze or something like that, and sort of like freely behaving animals. So what we did to this Miniscope is we added our diffuser, or it's just a phase mask now because we sort of designed it very carefully. So this is like a designer diffuser phase mask. So you place this at the back focal plane of that grin lens objective. We took out the tube lens and then we put our sensor here. So this is just like the DiffuserCam architecture, but now there's a beam splitter in there and some fluorescent filters so you can do fluorescent imaging. And we designed it for a few microns resolution so that we could see individual neurons but get a big enough field of view. And we can achieve our 3 micron goal that we got. Here's some raw captured videos from this Miniscope, and then the reconstructed images of these little tardigrades. They're like little caterpillars in the water. And our collaborator Salcedo at UCSF is studying their locomotion and was really excited to be able to have this high resolution across a big area with fast enough, like single shot 3D imaging so they can look at the dynamics in time. Okay, so the next thing, sort of like 3D function that we went after was time. This was the brainchild of a student in my group, Nick Antipa, who now has his own lab at UCSD. And he worked on this with undergrad Patrick Orr for a summer. And what they did was they showed that, I'm missing a slide, no worries. They showed that you can take advantage of the rolling shutter of your sensor to get a video reconstruction from a single raw frame captured with the rolling shutter. So the idea is that that because the rolling shutter only measures one line of the scene at a time and is quickly scanning through all of the rows of the image, then because you have a multiplex measurement where every point in the scene maps to every row of the sensor, then technically every row of the sensor contains information about the entire two-dimensional scene at that time point. And if the scene is dynamically changing faster than your row scan rate for your sensor, then you can think about trying to reconstruct a 2D scene from every row. And if you can, then every row can be measuring a frame of a video. So you get a single raw frame, and every row contains information about like the entire 2D scene at one time point. And so you get like 1,000 times faster frame rate because you can reconstruct these. In here here we're just doing 150 frames from a single raw data frame. And it's this is like a Nerf dart hitting an apple sitting on a textbook. So this is a highly leveraged compressing problem. It runs into noise issues, and you have to solve it as a big space-time 3D cube, not really trying to solve per 2D image from a single row. That won't work very well. Okay, so then the last one that I'll talk about is hyperspectral. We take our DiffuserCam, so diffuser in front of a sensor, and we make a single hardware change. So the hardware change we make is that we place a color filter array on top of the sensor. These are made by Vivo Solutions, who Christina and my group met at a conference and started this collaboration with. So they make these filter arrays. So it's a like an array of filters, like they're made with fabric pro cavities, and each like what we call superpixel. So each superpixel within this array contains filters that cover an 8x8 grid of filters that cover 64 color channels. So each pixel in the superpixel has a nice sharp bandwidth that covers a different wavelength across these 64 different wavelength channels. So basically, like each superpixel measures 64 channels of spectral information. And they built this thing to be used basically with a low resolution camera. So you would take a camera and basically like kill its resolution such that its point spread function was the size of the whole superpixel. So now you only have, well, in this case, like a 5x5 spatial information, but you get 64 color channels. So you would directly trade spatial information for spectral information to do hyperspectral imaging. So Christina's idea was that if you put this into the DiffuserCam framework, then a point in the scene maps to this large point spread function, which hits all of the different spectral filters at once. And you can do this compressed sensing approach, exactly the same reconstruction algorithm, but now you're solving for X, Y, and lambda. So you can treat like all of the other spectral filters as erasures and try to solve each color for a higher spatial resolution than the superpixel would allow. So we get about 0.2 superpixels resolution, meaning that we get 5 times higher spatial resolution than the nominal design for this type of spectral filter array, and we get it across these 64 color channels. So I think this is a really fun direction to go in, because these things can be cheap. They aren't cheap to buy one, but if you were to mass produce them, you could make these filter arrays $5, and they're totally customizable. So you can choose whichever spectral filters you want. You can have different array sizes. You can have different, you can add different colors together. And I think it's really interesting to think about designing these for a particular application. And the whole thing is really compact. So it's just the diffuser on top of the spectral filter array on top of the sensor. So you can make these compact, cheap, hyperspectral cameras that have pretty good resolution in both the spatial and the spectral dimensions. We're exploring a lot of different applications for that. This is one. This is these lanthanide beads. So we work with Polly Fordyce at Stanford, who designs like different beads with different spectra, and then needs to distinguish them in her microscope images. And so we can get okay spectral information, but with very good spatial resolution, so we can see individual beads here. All right, so like that's the end of like all of these different possibilities to do. I want to get into one more thing that I always get asked about if I don't talk about it proactively. And people say like why a diffuser? Is the diffuser the best encoder? Why not design a fancy optimal encoding scheme for this? And actually the diffuser is a good encoder. It's not the best. But if you think about it, these diffusers that we use, there are these like Gaussian engineered diffusers for this particular image, although Scott's shape gives you something pretty similar. But if you think about like they have concave bumps and convex bumps. The concave bumps are focusing light. So they're acting like little lenses, and they focus light into points or lines in this case. And so that is good. That's like concentrating light. So SNR wise, that's good. If you had a proper lens, you would do the most possible concentration. You'd take a point and you concentrate it all the way into a single point. So SNR wise, that's better. If you want just like the best SNR, so really noise limited imaging, then you should use a lens if you can. So we're spreading out the light, and that hurts us noise-wise. But if you think about a regular lens, when you go off focus, if you're trying to do 3D, yeah, you get a different signature for different depths of the image, but it's really just blurring. And this is really hard to compute, to do an inverse problem on. You can't computationally undo and get 3D information. And this is a bad PSF because it's like spread out and it just doesn't have the high spatial frequencies that you can have here. Whereas here, when you move different depths, you just get different stick patterns, scalings. So, so if you want to do like this 3D, then the spread out PSF is useful, and you don't have this like blurring out. So the multiplexing helps. It allows us to do compressed sensing. So we want the multiplexing, but we also do want concentration. We want the light. We don't like all of this like non-zero stuff in between the sharp edges. And that's all caused by these convex bumps here. And so what you could do is you could put a lens array instead of your diffuser, and that would concentrate the light so that you'd really have black in between all of these sharp points. And so that helps concentrate the light, but it keeps it spread out. So you're still spreading out the light a little bit across all the different points. And that's pretty a problem. And this has actually been done in the context of microscopy, called Fourier diffuser, I think Fourier light field microscope. And so the problem is that as you shift your point in the scene, then your point spread function, which is now a grid array of dots, it shifts. And when it shifts by one period of the grid, what happens? Then you get this measurement that's for this point source and this point source, the measurement is almost exactly the same, except for this one row of dots here. And so you have this like ambiguity where like, this is not good. This is hard to tell these 2 points apart. And so in the Fourier light field microscope, the way they dealt with it is just to say, this is your field of view, don't go beyond it. And then you won't have this ambiguity. But we didn't want to give up our field of view so much. So we say like, actually, if you use randomly spaced microlenses, then you get a randomly spaced set of dots. So you get the multiplexing benefits, and you don't have this ambiguity due to the periodicity of this like microlens array PSF. So now when we shift this randomly spaced microlenses, we don't have this like ambiguity, so we can keep a really big field of view, and this will all work. Moreover, our randomly spaced microlenses should each have different focal lengths so that we can get sharp PSF information at every depth. And so you can just put random multifocal microlenses. And that's how we started out with our like sort of our heuristic optimal design. But computational imaging has gone in this end-to-end imaging direction. That's really exciting about like, don't just optimize the algorithm to solve for the image as best as possible from the measurements you've given it, but start to optimize the optics. Put into a huge optimization problem how to design the hardware in the best way to get the most information into your measurements so that your algorithm can get the most information out of those measurements. And you do this like algorithm and hardware design together in an end-to-end fashion with these really large neural networks who are needle in a haystack type solutions. That would so here's an example. This is the diffuser surface. This is like the surface shape of the diffuser for having the diffuser in Fourier space. And this is the unrolled neural networks. And we're learning the best surface shape for this diffuser. It's a bunch of random microlens arrays. So we start out with our heuristic design of random microlens arrays. And you can see as you go through the iterations, then it gets better and better and better. And eventually the performance kind of levels off. And this is basically its design, which is kind of what we expected, you know, a bunch of microlenses that are randomly separated. And this is all designed for a particular 3D object. So it's going to be optimal for sparse point sources in 3D. Computers and optics should talk more. I think there's a lot of really interesting stuff happening at this intersection between hardware and software. And there's a lot of things that can be done by people who know both the hardware, like the optical engineering, and the software, inverse problems, neural networks, etc. We do a lot of work on what we call reproducibility. For computational imaging, reproducibility doesn't just mean putting your code open source, which we do, but also it means designing for systems that are cheap and simple. So making systems that people can replicate very easily so that they will adopt our approaches and don't have to spend hundreds of thousands of dollars to get this extra functionality. And we push really hard on this, and I think this is one of the things that computational imaging is very good at, is doing something that could already be done, but doing it cheaper, easier, faster, better in some way. So last thing I'll do is just plug a new tool, fairly new tool, that Henry Pinkert in my lab developed. And it's for people who use Micromanager, which helps control your microscope to automate your data collection. This just puts it all in Python so that you can use Python to do all of the neural network and image analysis stuff that's becoming really popular now. So with that, I will thank my group who did all of this work, all our collaborators, and my 2 anti-collaborators that are downstairs screaming at their grandma.
So, okay, thank you, Laura, for this fascinating talk. That really exemplify here the spirit of ISCS. So this is like hardware, software, co-design. So I'm sure that there's some questions for you. Okay, so, and please, to make it easy, just state your name.
Okay, thank you, Laurent Jacques here from UC Leuven in Belgium. Thank you for this very interesting talk. Plenty of examples related to computational imaging. So my question is about the last part of your talk when you explained this optimization of random lenses configuration. So I was just wondering if you consider the caustics you have with the diffuser, if it could not be already considered as a random lens configuration.
Yeah, it definitely is. So this idea of like using micro lenses rather, like, so I think of a diffuser has like positive bumps and negative bumps. And the positive bumps are helping you because they're concentrating light. The negative bumps are just spraying light, like creating like sort of like baseline, like washing out your image. And so it's basically a micro lens array is like only positive bumps. There's no negative bumps. And so that's good because you're not then like just spraying some of the light out and like spreading it out evenly, because that just creates like sort of like background haze that's not helpful for SNR. Does that make sense?
It's better here to have points that are, sorry, that the focalization of the lenses are really points and not lines like with the DiffuserCam.
Yeah, so that's a good question.
So, sorry.
So in this case, it is it's like it solves for it, so it is. And I'll say it probably depends. So I think that for like the hyperspectral case, the lines might be better than the points, but the points concentrate the light more, so they're better for SNR. So if you have a situation with lots of noise, then the points are going to be probably better than the lines, but the lines give you more multiplexing. So they can be good too if you're doing some highly leveraged thing where you're trying to like get a lot out of the compressed sensing, like solve for a lot more things than you measured. And so there's a trade-off there. And I think this particular application we designed for with the neural activity tracking, it's actually quite dim. The fluorophores are pretty dim. And so it goes for the points because that helps you with SNR versus the lines.
Okay, thank you very much.
Yeah, so there's a group at Rice that does a flat scope, and it's a different design because they put things a lot closer. It's more like a diffractive optic, so it's like has a bit of a different model. But they came to they use like these lines. It looks a lot like our diffuser, but it's like contour lines that are designed. But this performs better. Like the points will perform better for this case. Like in most cases where you have SNR is important.
Okay, does anyone else has any question? Okay, Amir.
I can't hear. I heard something briefly.
Can you hear me?
Yeah, I
Try
can hear.
again. Oh, sorry. So I repeat my question again. So I was wondering if you could recall in your forward model, what kind of noise model did you consider? Was it the Gaussian noise or Poisson noise? Just before unrolling the optimization step.
Yeah, we've looked at both. I'm pretty sure that stuff I'm showing is assuming Gaussian noise. You could look,
And
this paper was a while ago, so you could look in the paper, but I think probably this is Gaussian.
I see. What kind of considerations would you suggest for people trying to like consider Poisson noise in their model and then unroll the optimization?
Yeah, so Poisson noise basically means you have really, really low light levels, that you have a lot of noise generally for like modeling sensors. And so like multiplexing is not good in that case, right? Like, you might, like this might be a really tough like cell to make, that like you might want only like very few points in your point spread function. But you can do it, you can do this unrolling. I actually don't know how you would incorporate that into this unrolling. That would be a great question for Christina. She knows this a lot better than I do. Yeah, I don't know how you would incorporate that.
Thank you so much.
Okay, do we have any other questions, maybe online? So Amir, can you read it out?
I think Laura herself can also read the question if it's more convenient.
Yeah,
if not, I will
so
read it. Yeah.
what are the timescales on your reconstruction methods? How quickly do you recover an image from the sensor measurement? Okay, so that depends a lot. So for like the 2D imaging stuff, it's basically just a deconvolution. We do it iteratively with this regularization. So like the more iterations you do, the like more refined your image might get, but really marginal returns at some point. But we do all of that, like you can do it real time on a PC, like you can do it at the same frame rate as the camera. The 3D stuff is much slower. So we're talking like minutes for a large reconstruction like that leaf one, which I think was about 100 megavoxels. And again, it's like an iterative algorithm with like the more iterations you run, the better, but also it takes longer. So yeah, it depends. And then the neural network stuff is really fast. Like I showed some of these timescales. This is for 2D, but for 3D, you can also run it pretty. You could do it a lot faster with these neural network approaches. That's like, I think, the main benefit of using the deep learning stuff. But most of it is like the 3D stuff is mostly not going to be real time. I suppose you could do it real time if you paid a lot of money to Amazon Web Services, but we haven't tried that.
Okay, do we have any other questions? Okay, so I have one. So if one wants to do the DiffuserCam that you showed at the beginning, and if you want to go the only physics-based route, so you need, I guess, to estimate the point spread function from your diffuser. And then is this like really complicated to achieve? Is there like some kind of trade-off where you simplify the acquisition, but at a cost in some kind of calibration, or still it's pretty easy to do?
It's really easy. You can, like, you literally just put your iPhone flashlight in far away, like a few meters away, take a single picture and you're done. You might take like 10 pictures and average them just to make sure your point spread function measurement doesn't have much noise or has less noise than your measurement. But yeah, it's not a problem.
Okay, and when you do the deep unrolling, do you still use this calibration or you learn it again?
We use it.
Okay. Okay, thank you. Still, is there any other questions? Otherwise, okay, so I think we can all thank Professor Laura Waller, first for presenting to us, but also to bearing with all of the technical issues that we had. But thank you.
Thank you. It was fun. Enjoy the rest of the workshop.